thanks a lot for having me. Thanks for joining this talk. So I'm going to present on adaptive combinatorial allocation, or I guess now slightly more smoothly titled learning by matching, which is a joint project with Alex Teitelbaum. So kind of just by way of big picture background for this, I guess part of what got us started thinking about this topic is thinking about the ethics of experimentation, which especially for economics, so I'm coming from economics, is a relevant topic in the context of field experiments, say in development economics and other fields. And so the same is true also for active learning of various forms like banded algorithms and so on, which often involves experimentation in social contexts. And so this is in particular a salient question when there are vulnerable populations who are affected, which raises the question when it is ethical to experiment on humans. And so I like this Kant quote in this context, who argued that one should always act in such a way that you treat humanity, whether in your own person or in the person of any other, never merely as a means to an end, but always at the same time as an end. So kind of translating that into the context of active learning settings, I think is a strong case for designing algorithms that maximize participant well-being, as opposed to just using participants as a way of gathering information through experimentation. And more concretely, the setting that we're interested in this project is refugee resettlement, where at least in the United States, this is done by resettlement agencies who typically have a fairly small number of slots in various locations. So there's a lot of capacity constraints in different places. And traditionally, refugees who didn't have prior ties to the host country would just be distributed randomly without any regards to whether they would fare well in the locations they're allocated to. And so this is a topic that various co-authors, including Alex, my co-author in this project, have been working on before, and also in the context of this NGO anymore. And what they have been doing is to use historical data to estimate refugee location match effects. So kind of trying to understand which types of refugees perform well in which locations in terms of their labor market success in particular. And then based on these historical estimates, find the optimal matching and actually implement it with this agency HIAS, which is one of several agencies doing resettlement in the US. And what we're considering in this paper is kind of trying to incorporate the learning process into this whole resettlement process. And in particular, that leads us to an adaptive combinatorial allocation problem, or learning by matching. But the idea is refugees and locations get allocated to each other, and that involves a lot of feasibility constraints. But there's the demographic composition of who arrives in a given time. There is the number of slots available in different locations, legal restrictions on refugee resettlement. I mean, on a global scale, these quotas are pretty small. And typically the returns of the different matches are unknown, and you have to make this decision repeatedly. And so these features of the allocation problem, we think are typical of a lot of economic settings, in particular matching type problems, where you have to allocate different sides of a market to each other, and you have some outcomes you care about maximizing. And what that leads us to is effectively what's called a semi-banded problem. But so this is not a typical multi-armed banded problem, because we can't decide about the location we send refugees to independently across different people, because there are all these capacity constraints and other site constraints. So we have to decide on the entire allocation jointly rather than on the match one by one. And so the way we then model that, kind of drawing on this literature on semi-bandits, I think there are J possible matches. So those are all possible combinations of refugees and locations. And then action we have to choose in each period, say each quarter or each month, is to choose at most M matches. So if there are M refugees arriving, then we choose M out of the J matches. And before the next period, we then observe the outcomes of every chosen match. So for instance, whether they found a job at the location they were resettled to. And then there's a reward that we're trying to maximize, which is the sum of the outcomes of the chosen matches. And the objective is to maximize the cumulative expected reward. So again, this is very similar to a multi-armed bandit, except there are all these cross constraints on the allocation you can choose. And so we can formalize this by saying that there is this binary vector A that we have to choose, where AJ is 1 if that particular match gets realized, and then the entire vector kind of captures the entire matching. And the corresponding reward in expectation is the inner product of A and theta. And so if we were in a banded setting, all that we would observe is the overall reward. But what makes this a semi-banded setting is that we don't just observe the overall reward. Instead, we observe the rewards corresponding to the individual matches. So not just the return of the entire matching, but the return of each match. And that means we have more information, so we can potentially learn more quickly than if this was just a banded problem. And the algorithm we're implementing is Thompson sampling, which basically just picks a particular allocation with probability proportional to the probability, posterior probability that that allocation is optimal, which is a well-known and old algorithm for banded type problems. And now in this context of what we can do, just this kind of the theoretical part of our project, is building again on related existing results, derive a regret bound for Thompson sampling for this type of adaptive matching problem. And so again, what makes this interesting is that there are these cross constraints, which means that we don't just like independently choose the matches. So it's a harder problem than the banded problem from that perspective. And also, and that's what makes our result different from the existing results in the literature, is we are very much interested in priors where there is dependence across the components of theta, right? So if a particular demographic group of refugees does well in some locations, chances are they're also doing well in other locations. And similar, if there are a lot of jobs at one location, a particular group, there is also going to be a lot of jobs for other groups. So there's really all these statistical dependencies that we want to build into a prior, and that the regret bound would have to take care of or to take into account. And so this result delivers that. And I think this result is interesting in a number of ways. It holds infinite samples, there's no remainder. It's true for any prior. So it doesn't depend on, allows for any prior distribution across the thetas, in particular dependency across the components. It implies that Thompson sampling achieves the efficient rate for base regret. And furthermore, it implies that the worst case expected regret per unit goes to 0 rated 1 over the sample size, which is essentially the same rate you would have if there is no cross constraints. That's what's kind of, I don't know, to me was striking about this result, which I didn't anticipate, which is, so if you look in the regret bound on the right-hand side, there's T times M. M is the number of matches in each period. T is the number of periods. So we have a square root Tm over here. And so then the per capita regret in expectation goes to 0 at 1 over square root Tm. And that doesn't depend on the number of possible matchings and all these cross constraints, right? So the number of matchings is J choose M here. And if the cross constraints is a bit less, but that's growing exponentially. However, if that doesn't matter, it just matters how many matches there are overall. So in a way, despite the cross constraints, this remains a comparatively easy learning problem. And so in my remaining minutes, let me talk about kind of taking this to the data. In particular, for now, we've done simulations and we use this data by this resettlement agency HIAS for all refugees between 2011 and 2019. We classify refugees, or this is the primary applicant for relocation, into 8 demographic groups based on their age group, their gender, and whether or not they speak English, which tend to be all variables that are predictive of their labor market chances. There are 17 affiliates or locations to which refugees can be relocated within the US. So actually there are a few more, but the others have a small number of cases historically. So we are, for the sake of these simulations, we are ignoring them. The outcome we are looking at here is whether somebody got employed within 90 days of arrival. And so what we then do in the simulations is we take this historical data, we use them to calibrate the success rates for each combination of refugee type and affiliate. And then we take the actual capacity constraints, so in each given period, how many refugees different locations were actually allowed to accept. And then we do a counterfactual matching using Thompson sampling. So this also involves an integer programming step to find the optimal allocation for a given draw from the posterior, and maximizing expected returns. And so what I was mentioning before is that we really want to allow here for prior distributions that take into account the dependency across different possible matches. And so here the types of refugees are U, the different locations are V. And what we want to allow for is that there's statistical dependence for the same U across different V and for the same V across different U. And then there might also be idiosyncratic match components in the prior. And so one easy way of writing down a prior like this is like the following, where the expected success rate for each type of match is theta J, and that's distributed with a logistic that has a refugee type fixed effect, a location type fixed effect, and an interaction effect, each drawn from some hyper prior distribution. And so when we implement that, and then again, in the simulations, we take the actual capacities of locations and the actual arrivals of refugees, and we simulate successes based on the historical success rates for each of these match types. And this is what we get. So we start the algorithm in 2011, and there's some constraints here that refugees with prior ties have to be relocated to where they have their prior ties. So if you already have family in a city, you get sent to that city. And essentially what you see here is this is running multiple simulations. Each simulation trajectory is one of the gray lines. The actual assignment that we have historically is the red line, and those are the expected returns. And so you see variation across the years because the demographic composition of arrivals changes over years. Oracle optimum is the best possible we could hope to achieve. Basically, if from the beginning we knew the success rates for each combination. So this is picking the optimal allocation given knowledge of the vector theta. And then you see that Thompson fairly quickly converges upward and over time approaches the Oracle optimum as we would hope here. However, there's a bit of a twist here in that this is not a uniform improvement across groups, which is something we didn't really think about hard ex ante, but then once we started the simulations became obvious, and it's something where one might want to rethink hard what the objective function is. And so in particular, what happens here is that there are some demographic groups who have low chances to find employment to begin with. And so sending them to better locations doesn't seem to matter as much. And so what ends up happening in the algorithm, in the simulations, is that Thompson sampling on average leads to large improvement relative to the actual assignment. But there are some groups who actually lose out. And in particular, these are both men and women who don't speak English and are not of working age. Those just apparently get sent to worse locations by the algorithm, because if you just want to maximize the overall employment rates, it ends up sending the refugees with higher employment prospects to the better locations. Yeah, so this is something one might want to take into account in kind of maybe changing the objective function relative to what we did here. And so I guess our hope down the road is to implement some variation of that in practice with any more. And I will stop here. Thank you very much.
Thanks, Max, for a great talk. I think you have a couple minutes, so we have a couple more minutes to dig into questions. Duncan's already sent a great question that I'll read out loud for the benefit of the audience. Question for Max: why focus on 90-day employment? Are there other measures of success for a match?
Absolutely, there are other measures. Part of the reason we did it was just to be in line what they've done in these previous non-adaptive implementations. Part of the reason was to have an outcome that's realized fast enough that we have a quarterly assignment, we get the outcome. But those are not very good justifications at the end of the day if you actually take this to a real implementation, I think. And yeah, I mean, in my opinion, if we take this type of algorithm to the real world, probably the most important thing is to really think hard about what the objective function is, what we try to maximize, and what might get lost if we maximize the wrong objective. And so of course, we care about other things than labor market outcomes. And it might also be that 90 days is too long or too short. Yeah, so good question, I guess.
Great, and just as a reminder, we've got another question in chat. Please post your questions in chat or with the Q&A function. So Stefania Ionescu asks, was the original algorithm implemented in practice?
Yes, it was. So I wasn't involved with that, but they did, basically what they did is take historical data, essentially run a big lasso regression to predict match-specific returns, and then just statically take these estimates for allocations going forward within hires. So they have actually done that. Of course, there is a bit of an issue here that well, let's not get into it, but there's exogeneity is assured if you actually run an algorithm like this, which might not be the case for historical data.
Another question from Paul Golt. Does your algorithmic approach extend if the employment is only observed with a delay?
Yeah, I think it does. And I think that's one nice feature of doing Thompson sampling in various settings is that it's very versatile, right? So essentially you can, if you have whatever model and whatever way of updating your beliefs, you can always form a posterior belief that's optimal at a given point in time. Oh, sorry, it's the correct Bayesian posterior belief at a given point in time, and then just use that in order to draw a vector's data from the posterior and find the corresponding optimal allocation for the draw from the posterior. And so this involves like if there's like overlapping waves, or if there's delays in observation, or if you combine various outcomes, all kinds of things. So in terms of implementation of algorithm, it's easy to extend in all these directions. Extending the theory might be a little bit more subtle, but.
Great. Thanks everyone for these questions.